All right, so this was the one that we were having a trouble figuring out during session. So I already drew out our diagram here. We have an electron that's entering these parallel plate systems. We know that there's a distance of 0.065 meters between them. We know that since it's an electron, it's going to be attracted towards that positive terminal of the parallel plate. So it's going to kind of shoot up as it passes through this system. What we're specifically asked for is, what is this angle right here that it makes upon exiting? And because it's attracted to this plus side, we know there's a force, and that being the electric force pointing straight up. So here we can draw a coordinate system. And because we're going to be looking for that angle, it can be extrapolated two ways. Well, first off, we know we're going to need vectors, right? So that can either be through forces and fields or through velocity. So here we can, because there's a velocity direction, right? Here we can see that the forces don't cut it, right? There's only a force in the y direction. And then with respect to the x direction, there are no forces. The field itself is pointing straight down, so there's nothing else there. So that's why we're going to use the equation of PE is equal to KE. So potential is equal to kinetic. If we recall, our potential energy equation is equal to Q delta V. And since we're working with velocities, we have 1/2 m v naught x squared. So that's that initial velocity. If we do some rearranging for what we're solving for, which is that v naught x, you can see that v naught x equals the square root of 2q, that final potential minus that initial potential over mass. Okay? The initial is equal to 0. The final is equal to that 2,200. Was that what it was? 2,200? Yeah, because it starts at rest and then goes to 2,200. We now can solve for v naught x, which is equal to 2.78 times 10 to the 7 meters per second. Okay? So because there are no forces in the x direction, by definition, there's no acceleration. Because there's no acceleration, this tells us that the final velocity and the initial velocity are equal. There's going to be nothing that's going to change the velocity of this electron in respect to the x direction. What we can do now is move into looking at the y component, right? Because with the x and the y, we're going to be able to pull out an angle. What we can say is v f, this is like a kinematic equation, equals v y naught plus a y t. So that's the acceleration in the y direction. Initially, it just enters, on this horizontal plane. So there is no initial velocity in the y direction, right? The force over here doesn't start until it enters this point. So the initial is equal to 0. What we're left with is ay and t. Both of those are unknown. So the first thing I'm going to want to do is solve for ay. And if we use Newton's second law, we can see that F, like the sum of forces in the y direction, equals may. Because we're dealing with the electric force, we talked about last week, which equals EQ, we can plug in EQ. And now this is where we use that specialty equation. That specialty equation we can rearrange to make E equal to V over D. So therefore we can plug in everything together and we'll get VQ over DM equals AY. So that's going to be like some rearranging there. That leaves us with something we can solve. We can plug in AY. And then next is T. So T is equal to the change in position over the velocity it's moving, right? And I'm going to go with the X, but you can also go with the Y because they do give you how wide they are. So that's going to be equal to 0.065 divided by, that 2.78 times 10 to the 7. And all that comes out to be equal to, let's see what we have here. 2.34 times 10 to the minus 9 seconds. Okay? So at this point, you now have everything you need to solve for that final velocity with respect to the y direction. So we'll say VYF equals VQ over DM times T. We just found out what T is. You're going to plug in everything you need, and you'll end up getting 7.9 times 10 to the minus 6 meters per second. So let me be clear here. This is where the confusion stemmed from during the session. Because there are no forces in the x direction, there is no acceleration. Therefore, the initial velocity upon entering the parallel plates is equal to that upon exiting. Conversely, since there is a force in the y direction, you're going to need to acknowledge that force per the difference, per its acceleration, right? There's going to be some acceleration in the y direction because it gets it from, this constant right here, and then it gets it moving up. So now we have a comparable element, which we can combine with the the final x velocity to be able to extrapolate a vector. So, we can draw this as, let's do v fx, v yf, this, put a theta here. We're going to use theta equals tan inverse. We're going to plug in our y, so 7.9 times 10 to the minus 6, divided by 2.78 times 10 to the 7. You're going to do all that, and you're going to find the answer is 15.9 degrees above the x-axis. All right. So again, kind of key highlights here are we need to be able to find an angle. That angle is found by using, the forces or fields. You can establish, like with your coordinate system, a final and initials, and you can pull out an angle. The other way you can do it is with velocities, right? We have an initial and a final x and a final y. The other thing I want to note here is when there's no forces in the direction, there's no acceleration. Therefore, the initial velocity is equal to the final. That's the converse where there is a force. And the last one is this special equation that we use right here. So we set the electric force equal to EQ. You'd be like, wait, how do I solve this? I don't know what the electric field is. You have to remember that E equals V over D. And they give you, they'll give you the potential difference between the plates in the question. Okay. I hope this clears this up. I apologize for forgetting kind of how to solve this one. It was very embarrassing. I biked home as fast as I can to get this out to you as fast as I can. All right, thanks.